Okay, now here we are again, having just proved or gone through the proof of one of the major theorems of geometry. Something I doubt that certainly the Egyptians would not have been able to demonstrate, and probably by this time would have been taking notice of the so-called stupid Greeks in their stupid ways, who are coming up with puzzles to riddles that the Egyptians could only dream about. We have shown, Euclid has shown the using the isosceles, and I'm going to keep my mouth shut from now on when I say that it looks like we're done with something. He was certainly not done with that isosceles triangle. Using the isosceles has shown the uniqueness of all triangles in terms of their lengths, independent of scale, without appealing to symmetry, without appealing to without appealing to I don't know, measurement, definitely, without appealing to anything really. That result has been established. No, there was something else I wanted to say about that. Appealing to. There was another thing that was not that one might think would have been required to get to this stage. Oh yes, no appeals to the sum of angles, adding up to anything. No appeals to the sum of angles of a triangle adding up to anything. None of these things were necessary to establish this fact. Okay, and yet it's been established. We still don't know anything about how to bisect a line, how to form a right angle. Anything like that has nothing like that's been demonstrated, as it turns out. It started with an equilateral, construction of an equilateral with two circles, right? And our straight edge and compass. And from that, a method for copying a given line to another place. And from that, the demonstration of that two equal sides having an equal angle give rise to a unique third side, and then the isosceles, all isosceles are characterized by having equal base angles and vice versa. And now all sides being equal defines a unique object independent of scale. And now the next. We've got all that. What could possibly be missing? If two triangles have two sides, one of them respectively equal to two sides of the other. Two triangles have two sides of the one okay. Now when he writes this, that means two triangles have two sides in respective order, but of course out of three things, everything's restricted, right? Well, no, let's see. If this was red, blue, can I get it by rotating? No. So there's a difference between, there is a directional thing, which, even with triangles. If I say red and blue are equal respectively on the two triangles, that implies this picture. It does not imply the picture which would have a blue here on the bottom, because I can't, although maybe I'm allowed to flip it over, but I don't think I'm allowed to flip it over. Nothing in the axiom says that you can flip things over. You can place things against each other, but flipping, no. So there's no way for me to place, there would be no way for me to place another one with red and blue like this on top of this one and have them coincide. However, that's not the case here. The sides being assumed to be equal are equal in the same order, and their bases also being assumed to be equal. From that, we wish to obtain the following result, that the angle, one of the angles anyway, are equal. Okay, one of the corresponding angles, the top one appears to be equal. Now it seems to me like if you can show that, then you can say the same thing about all of the angles. But let's just take it as is. I'll write it down in my shop here. I've written down the text. So we have two triangles. Now I don't want this back now. I want a darker one. Yeah. I like this one. It reminds me of, I don't know, Middle Eastern kind of feel to it. Okay, so we have the reds and the blues. Red. And the base, white, being equal. So let me just draw the two triangles. Red, and I'll just duplicate that. Makes my life easier. And blue. And the base white. All of these sides are being given as equal. Right? Two triangles have two sides of the one equal respectively, not equal, to two sides of the other, red and blue, and also their bases, which I don't know how the base is supposed to be defined, equal, and the angles, that's this and this. I don't know if we'll fit, so I'll use my special tool. These ought to be equal. Now that seems pretty obvious, but let's go through the argument. If the equal bases be conceived to be placed one upon the other, so the triangles shall lie on the same side of them, and that the equal sides, red and blue, be coterminous, so ending at the same place, right? I'm going to save this and make a copy of it. Then I want to modify. And I want to try to do what he's saying. So what we're trying to do, similar to before, we're going to place the bases one on top of the other, and we know that they're the same, so they will coincide, the bases, and it's like we're moving this, let's say, this way. Right? So we're bringing that thing together by pushing the base together, and so that the triangle shall lie at the same side of them, same side of what? Oh, of the bases. So on the top, we could do it upside down, but we're doing it not upside down. And that the equal sides, red and blue, be coterminous. And that much we can be sure of, because this point, this line is completely coincident with this one at all points, and in particular, these 2 points. Call this P1, and call this P2. And by the way, this program, if anyone wants to use it, I can make available. It's kind of something that I made for fiddling around, so it's not a commercial product. Something that you have to expect won't work perfectly in every case. The P4 is underneath there, but it might help if you want to do the same things. Okay, now so P1 and P2 will be together, and same with these 2. Alright. Now what does that tell us? The vertex of one must fall on the vertex of the other, for suppose them not coincident. The vertex of one, I think it's talking about this point now, must fall on the vertex of the other, for suppose them not coincident. We would get a contradiction as follows. Red coincides, therefore, besides red and blue being coincident with red and blue, I'm not sure if I read this right. For suppose them not coincident. Let me try this from the beginning. If the equal sides, white in my case, be conceived to be placed upon the other, so that the triangles shall lie at the same side of them, and that the equal sides, red and blue, be coterminous, at least coterminous. The vertex of the one must fall on the vertex of the other. For suppose them not coincident would contradict the last proposition. Oh, okay. He's just saying what I just said. They must be, these vertices must be coincident, because this is coincident at all points, including the end points, where it meets with red and blue. Therefore, the sides red and blue being coincident with the reds and the blues of the other triangle imply coincidence all the way uh, along both sides. I think that follows kind of trivially. I can't see if there's anything left to be shown. We know that, yes, we know that these must be coincident from the last theorem, right? Because the sides red and blue resemble this diagram, right? And in this diagram, the vertices were not able to be placed other than upon themselves. So therefore the apex must also be coincident, and the whole thing is coincident, and therefore this angle and this angle are the same. Now, that was pretty easy. I think we'll just go to one more. Therefore, this equals, I don't think this one is, I think this one, this doesn't really count as a theorem. It counts as I would call this a corollary, a minor consequence of the last theorem. Okay, now this one is not a theorem at all, it's a problem. Alright, we'll try and do it quick. Okay, I'm interested in this one myself. To bisect a given rectilinear angle. Okay, so now this is book 1, prop 9. Book 1, 9, 0, prop, I guess. How come I got that all the other ones disappeared? Didn't have a number for the proposition. Oh, it's not a proposition, it's a problem. That's why. I don't know. It doesn't matter about the number. We know where we are. So let's do as instructed. We take equal signs, red and red. The easiest way for me to do equal sides, and I assume they're going to be at equal angles. Just to use this thing, something like this length, maybe 100, rotated by, the rotation is that way, 30, or let's say 40 degrees. No, that's not enough then. But I'm rotating the world, actually, so it's going the opposite direction. Well, 40 negative should look okay. It's the same. 30. Let's see. I want to make it steeper, I need to add more. 50. 53. There we go. Minus even though it hasn't been stated, I'm assuming we're going to construct this in such a way that these angles are equal. Draw a yellow line horizontal upon which describe a blue. So draw a horizontal yellow line. Oh, I see. So these could continue on. Let's see what he's saying here. I'm going to do that just to indicate. Whoops. Oh, great. Get rid of that too. To try. I want these, part of it thick and part of it thin. Line mode with that, no bounding. Yeah. So we have a figure something like this. And now we're to draw a yellow straight line. 0. No, well, it doesn't matter. Okay, I prefer the next one to be thick. Okay, now the red lines meet. Describe these blue lines and then draw a black. Describe blue. Blue equals blue. Because red is equal to red, these have to be similar length, these reds, and they are by the way I drew them. But let me do it differently, just so that we're not kidding ourselves. Same length, different angle. Oops, same color. And that was a 75, was it? No, 100. Right? Now, these have simply been chosen equal in length. To describe yellow, we need to simply connect these points where they end, and knowing that they're of the same length. Bounded or not, we can do bounded. Alright. And now, from the corner, describe blue and blue. How? How are we supposed to describe blue and blue? Problem 1. Oh, I see. We're going to use problem 1 to make an equilateral out of this yellow here. Okay, so that means I need my circle. It doesn't matter what color, not pi. Okay, and another one here. Alright, and I'm going to draw blue and blue. By making an equilateral triangle with the yellow. Draw black. Black is just from corner to this corner to this corner. In that case, white. Oh, sorry. Okay. Because red equals red by construction, and white common to the two triangles. That's true. White is common to these two. And blue equals blue by construction. Then by problem 8, here, blue equals, this, here we have, this is the same. I'm going to use problem 8. It seems like, problem 3 and problem 1. Let's see what problem 3 was. Problem 3 was to copy. Like, it looks to me like, according to this diagram, these are two equilateral, not arbitrary. That is, I take one red, known length red line thing, I draw another one at the same point, which problem 3 allows me to do. I draw a yellow line to connect the two. Using problem 1, I make an equilateral. These will be the same length as this. I draw this here connecting the two figures. And red equals red. And this in common. This in common. Now what's blue equals to blue got to do with anything? Same base, but not same. This side is not the same. The reds and the blues are not the same, not by this construction. Surely it can be done now with an equilateral because of this result, right? If we have equal sides, we can claim equal angles. But this and this, oh, no. And black common to the two triangles. Red equals red. Oh, I see. Okay, I get it. I think I get it. It's this triangle and this triangle. So here we've got is that still white? Oh, wait, to copy this. This, and this, right? And on the other side we have, let me get rid of these. Here, this, and this, right? Now, if I get rid of this thing, put them together, like that, right? Then according to the last problem, we have these common and these sides all the same, right? So therefore we can claim, well, let's take this as the base, the blue one is the base, right? Follow through the last problem, and that tells us, without any thinking or anything, or appealing to any symmetry or anything like that, this angle, that circle would have been filled too if I'd finished my feature. The last problem states that if we have same bases and same sides, then the angles, the top angle, whatever it is, whichever one we choose, will be the same, right? So therefore, these two angles are the same. Now, if these two angles are the same, then this triangle and this triangle are exact copies of each other, and so therefore this length has to be the same, right? And we finally honestly bisected the the line, the yellow line. Well, actually what we've done is we bisected the angle. So we took the entire angle, right? I should make this a different color, right? And in the original figure, with these two reds, we had a different angle. Let's say brown, right? And brown equals, let's see. This is great. I love this. This is so fun. Brown is certainly equal to this sum, right? And we've just shown that these two are equal. So we bisected the angle, not the line. We'll do that next, I guess. Bisected. So we bisected that. Amazing. Brilliant. Okay, I should probably have split this into two drawings. I will. Okay, that's it for another one. See you next time. I just want to make a quick note that I'm sure that anyone watching and paying attention would complain that this is not exactly analogous to puzzle 8, where the sides being given were equal in respective order. That's not the case here, as it turns out. This is a mirror image of this. However, if you follow through the logic of problem 8 and look at theorem, this theorem, whatever number it was called, this one can be done upside down. That is, that the result of this theorem is established equally well with the same red and blue lines by drawing this top part on the bottom, which is a mirror image of the top, and there is only one possible set of reds and blues For the bottom part, that is, they can't be separated. The bottom image must necessarily be a mirror image of the top image. In order for them to coincide. Let's see now. We can't have them different, red and blue, right? And here, what we have is the same picture. If you rotate this image by 90 degrees and assume red and blue are different, right? And that they are copies, then you would get a contradiction. So there's only one possibility where it works, in which case red and blue are identical. Now, red and blue being identical on the bottom establishes the same comparison for this angle as for the mirror image of this triangle, because that mirror image is simply the mirror image of this one with the same lengths of sides on the bottom, if you know what I mean. I don't think that the order is important here. It just helps in demonstrating the coincidence of the vertices. But here, if you folded this, if you just take this part and if you folded it along the red, like if it was written on paper, and you fold this figure along the black line, right? Then you have all of these things lining up exactly because they are of the same length. And there's only one possible way to have things with the same lengths in this direction, let's say. That's arbitrary. And it would be the same if you went to the left or to the right. What would be the same would be that if this is red and this is black, this must be blue, right? If that's true on this side, then that's also true on this side. The symmetry argument works because this argument is symmetric. Yeah, about this baseline. We can apply this same. We just go back to this thing and see if it's possible for me to have black and blue the same and the vertex different, and the answer comes back no. So there's only one possibility. I think, I don't know. It appears to me that there's a slight difference, and I'm trying to find a way to explain to myself why we can get away with that, and I think that the reason has to do with the way that this argument has its mirror image LL. Maybe. I'll think about it a bit more. Okay, see you.